We have a few questions, maybe starting with you, Madhu, but it can be a question that can be addressed by many people. In your talk, you talked about standards of evidence for life signatures. And one step you mentioned is to ask whether life would produce a signal given the environment, its environment. Could you elaborate on the term environment? And maybe this is a question other speakers would like to speak about the environment of the Earth.
Yeah. So most of the time when we talk about, is this on? Yeah. Most of the time when we talk about biosignatures, we, for good reasons, are very focused on detecting that one molecule that we think is a good indicator of life on Earth. But what we most often also forget that the environment plays a big role in what kind of molecule becomes a biosignature. So for example, if you have oxygen, there are various studies that show that oxygen, while a good biosignature on Earth, can be produced abiotically in other environments. Same for methane, same for several other molecules. So it's very important to get the context right. And in detecting a biosignature, we also get all the other, at the end of the day, you're making a spectroscopic measurement, right? So that has a lot of information over the whole environment and how life, if there is life, reacts with its environment. So you'll get all that chemical information. So it is important to tease apart that information and extract information about what it tells you about, let's say, whether there is an ocean or geological activity or what the temperature is going to be like. All that information, which then puts that one molecule which you think is a biosignature in context. So that is part of the robustness measure when you try to understand biosignatures.
Anybody who wants to add something on the environment? No? Sean?
I really agree with Madhu, and the part of this for me is like the NASA guy is we have an operational definition for life that really goes back to the era when we were thinking about searching for life inside the solar system in situ, where we'd have a great amount of detail at the molecular level of both the life and the biosignatures as well as the environment. And that operational definition for life is a self-sustaining chemical system capable of Darwinian evolution, I think is the operational definition. How are we going to find that for an exoplanet? And I think the only answer is to do the things that Madhu was just talking about, to look at the environment at the global level with these spectra, and then ask yourself, like, what would a global biosphere do in that environmental context, and predict the biosignatures tuned to that environment. Because if evolution is occurring on the global scale on that world, the life should tune itself to the environment and do the most energetically advantageous thing in that context. So if you can predict based on the environment, the biosignature, and then you see that biosignature, it is operationally, and I also think philosophically, a stronger biosignature than outside the context of the environment.
Maybe just something to add for the context. I think it was mentioned in one of the other talks that you have to know the star in order to be able to interpret the spectra of the planet and so on. And I think what also showed in the discussion on the presentations today, we're really focusing on the stars within 5 or 10 or 15 parsecs for all of these future flagship missions in the US and also in Europe. But then I'm sometimes surprised that there's no systematic program to really understand these stars with the means we already have, right? There's no program that really monitors these stars systematically in the UV, for instance, or have systematic radial velocity measurements. Even if you do not find the stars, you're going to learn a lot what planets do not exist. And I think there's so much contextual information that we can start gathering with the means we have today available for all these systems. And I would hope that through the meetings like this and through having a truly international community, we come up with the understanding that we need to start these kind of programs that once those flagships are flying, that we really need to really understand the stars and the context that with the means we already have. And we're not done yet.
Perhaps just to add, I fully agree. And in fact, in the context of aerial, we are trying to join forces. The fact that we have a sort of global network at this point behind Ariel is important because we already started to monitor all the stars in the catalog, the ephemerides of the planets, anything that we can do prior to the mission, because of course you can still observe the planets if you don't have all that information, but chances are is that you're looking at the planets in the wrong moments because the ephemeride is not right. Or maybe it turns out that star has very different parameters, meaning that then planets will move in the diagram that you're shown about mass and radius, because everything we know about the planets is in units of the star. So if you don't know the star, then you don't know the planet. So I think it's exceedingly important to do that.
Concerning the context, we didn't mention that, but it's a question for you maybe. If you have the choice of characterizing Earth, would you choose Earth in Earth-like planets? Would you choose systems in multiple, an Earth in a multiple system with a giant, for instance, or would you prefer just a single system?
Who is this question for?
For everyone who wants to answer, maybe, yeah.
I'm just saying, I would say all of the above, if I can, because at the end of the day, I don't think of course we have tons of theories and great ideas. Whether these ideas are correct or not, I personally don't know, and so I would like to see the experiments.
Yeah, but imagine that you make an experiment and you want to visit one object.
So from a practitioner's point of view, we always prioritize the observability of the target. I mean, all things said and done, at the end of the day, you want the highest signal to noise. That's where the buck stops, so to speak. So that's what I would prioritize, even if it's a single planet system. If there is a habitable planet that is very good in terms of observability, that's what we'll prioritize. But then if you're asking, you have two identical systems with identical observability, then having the multi-planet system, gives you more information about the system, about the planetary system. So I would choose that.
Yeah, my question was rather in connection with life and with the water. Yeah. Do you expect the water to be? From
experience in the solar system, right? So you think like the presence of Jupiter helped the delivery of water to the Earth. So in that sense, you might have more information. Contextual information for life.
Any other comment? No? Anyone?
Yeah. So I have a question, I think, for everyone on the panel, but maybe I'll start with you, Becky. We've heard a lot about big missions, like the ELTs and HabWorlds and Life, and then about little missions like Ptolemy and Ariel's, maybe not little, but a lot of these missions have been in conception for a long time, but the biggest missions like Life and HabWorlds are only just starting to come together. So as you're on that bleeding edge of thinking about it, are you starting to wish there were stepping stones in between, that either technologies that are missing or missions that are missing that would get us there faster than just waiting until everything is working on the ground or everything is working at the 30-meter telescope?
Yeah, I think, okay. When it comes to looking ahead to the 30-meter class ground-based telescopes, as you saw from one of the figures I showed, putting today's high-contrast technology on a larger telescope doesn't solve all of our problems. And so each one of those technical problems, some that I mentioned like predictive control and others that we haven't yet discussed like coronagraph design, all of those problems can be addressed with the telescopes that we have now on the ground. And so to my mind, there's no reason to wait. In fact, we can only lose by waiting. I think we can start to develop all of these advanced techniques with the telescopes that we already have. And because that's where a lot of mature science instrumentation is, that's also what will get us even greater science benefit. I guess one more thing that I would add to that is I think we can, as we look ahead to a future mission like HabWorlds, we can also consider how can we use our current ground-based telescopes as test beds for the technology on those. So segmented apertures was one example.
I have a little bit to add on a pragmatic point of view. So my background is more from the space industry, commercial applications, technology, and something that I think we could do in more of a science community is bridge the gap between the science community's missions and the space industry's technology and applications. And I think that actually goes to one of the main objectives that Breakthrough tries to pursue, which is dragging us, the UCID School of Physics, into the new space age. And that's something that I've been able to help the team with. The space industry is always keen to find honest work, great missions to be a part of. And from what I've heard today, some of the missions that are being performed in science are the most exciting things for humankind. So like Sean showed us in his very last slide, some of the images from James Webb being displayed to the public. I think that's something that we can all work on individually, is trying to bridge the gap between the wider community and science missions so that we can actually start to fill some of the technological or funding gaps that we might be experiencing.
If I may add, one less appreciated gap in this area in trying to understand biosignatures is that I alluded to in my talk. At the end of the day, you want absorption data, molecular absorption data, line lists, right, for all these biomarkers. If you look in the literature, most of those are for Earth-like conditions. I talked about various molecules, but all of them basically have the line list for an Earth-like atmosphere and Earth-like temperature and pressure, usually for a few temperatures and pressures. What is missed in all the discussion is that when you're looking at these exoplanets, they're in all kinds of environments. And we actually don't have the line data that go into the spectral models that will then be used to interpret that data. So you can't actually guarantee that even if you're seeing a spectral signature, you can actually interpret it accurately because those data don't exist. And that has to do with a lot of lab-based experimentation. And people do this, chemistry departments do these sort of things. It's just that they've not been traditionally focused on the kinds of molecules that we are interested in. So some of the technology exists, some technology development needs to be done, but that is not well represented in the usual discussions about what it takes to detect a biomarker molecule. And I think we are relaxed about it because in our minds we think the biomarker detection will come in a decade or two. Eventually we'll catch up with the ground-based experiments, but we might be surprised. So I think that is somewhere to invest if there is a choice.
Maybe I can add just one quick thing for interferometry, because you're all probably more familiar with the direct imaging concept when you have the coronagraphs and take the pictures directly. And it was often forgotten that we have working interferometers on the ground. So the LBTI, for instance, had very important results to quantify the level of exozone levels around nearest stars. And this is a working interferometer. There's a Chara interferometer where now people think about using or developing another instrument similar to what a live mission would do. There's the VLTI, which is also an interferometer. Also there's a group or a suite of visitor instruments coming up. So similar to the ELTs that paved the way for HabWorlds, I think there's ground-based activities. And then what we would like to really understand if there's, as you said, a stepping stone for something like the live mission, right? A lot of people feel uncomfortable going from no exoplanet detected, with anything with something like nulling to such a thing, right? And in the course of the study I was mentioning that we're trying to kick off next year, we'd really like to understand if there's, a small, maybe, CubeSat, small-sat kind of mission that would be that stepping stone. At this point in time, we don't know what this could be, but there's certainly something on our minds.
Thank you. Does anybody else have anything to add to that?
Any question from the audience? Yeah.
So the LIFE mission and the Taliban mission both propose using groups of spacecraft flying in formation. How far are we along in being able to make sure that the formations stay in a stable organization, and does that limit the life of the mission because you need extra fuel?
So I just mentioned briefly formation flying as one of the boxes that we are very well aware it's very important, but that we don't actively pursue to the same extent as other points. And one of the reasons is that there's a technology demonstration mission from the European Space Agency, which is called Proba 3. And this is supposed to launch next year. And it's 2 spacecraft that are the size of washing machines. So this is already a good size. So it's not cubes, but it's bigger spacecraft. And the separation they have is of order a few hundred meters. So this also corresponds to separation we would have for the LIFE mission. And if they achieve their requirements, which is of order a millimeter or better, relative position, autonomously, and they also do maneuvers, so they disconnect and connect again. It's only 2 spacecraft, that's right, it's not 4 or 5. But if this would work, this would be a very important stepping stone towards increasing the number of spacecraft. So we're watching carefully what they're doing. We're also in touch with people from the LISA mission, the gravitational wave mission, to understand how they do their positioning. There's other activities in different groups dedicated to formation flying. So this is why we try to gather all the data and understand what is missing. But we're somewhat optimistic that this could actually work.
Okay, so yeah, my question's for Sean. In the context of life as we know it, you had this plot, and thanks for showing it, about how ozone is about 4 to 5 times more valuable than oxygen. So ozone's something that you see in the UV and the mid-infrared. But my understanding is that at 250 to 300 nanometers, getting 10 to the minus 10 contrast on stars that are very faint at those wavelengths is going to be difficult. So I haven't seen the justification for the 25 planets, but what would be the number of planets, or when do I see a refereed paper that says how many planets you would actually get that 250 to 300 nanometer ozone band?
So like real talk, that's tough. I mean, that's the hardest observation for, I think, one of these, for ultraviolet to near IR direct imaging mission, because of the reasons you state. One of the things that we're talking about is making sure that we're specific about what's the detection. And in the ultraviolet, if we're looking for that ozone band, one of the things that helps us is it's a very broad and very deep band, which means that what we're really just trying to see is, for lack of a better word, is it black? And is it black over this broad bin of points? Now, that still is going to be difficult, not just for the faintness thing that you mentioned, but if we want an internal coronagraph, which is the kind of baseline that we're looking at for the instrumentation for the starlight suppression, getting those coronagraphs to function in the ultraviolet is its own challenge, both because we haven't proven that can work yet, and because the reflective elements inside the coronagraph, of which there are many to correct the starlight, the wavefront errors, those are also going to make that faint thing even yet fainter. And to be like totally open and honest about it, it might be that the coronagraph isn't going to work down in the ultraviolet, at least not on a first generation instrument. It's more likely, in my opinion, and this isn't like any official thing, this is me like predicting, but being open with you all, like it's more likely to either be a second generation instrument or something that we decide we have to follow up with a different instrument, something like a star shade that would be paired with HWO if the internal coronagraph is the first gen instrument. Or we are looking at our colleagues like Sasha and saying we can't do it in the UV and we want to go out into the mid IR to get that confirming signal. So I think that's how I would think about it. In terms of the yields for the biosignatures, that paper, I would say about a year or 2 from now, we've got a couple graduate students working on that exact problem. And the way that they're taking that problem apart is they're saying, once you've done the detection, what are the specific observations you do to look for signs of habitability, like water vapor? What are the observations you do to look for a primary biosignature like oxygen or methane, and then or ozone? And then what are the things you do to look for what we would call a confirming secondary biosignature that constrains the production rate of that primary biosignature? So for oxygen or ozone, that would be methane. For methane as the primary signature, that would be carbon dioxide as the confirming signature. And while you're doing that, you're also trying to optimize the band passes you're doing that in, so that you get enough contextual information in the ways that Madhu talked about, so that you can rule out the known false positive mechanisms for life. We think you can do that in like 2 or 3 observations and get to the point where you could write a scientific paper that would create a huge debate and hopefully motivate the follow-up mission to resolve that debate. And I think we don't have the yields for that yet, but we know the strategy for getting there. We're optimizing the wavelengths for that now. And showing that strategy works. That's the first series of papers coming up from our team. And then the next series of papers would be, then showing what your yields would be. I should also maybe toss it to Sasha, because everything I just said is kind of for coronagraphs, where the challenge with the coronagraph is because it's so hard to maintain that wavefront. You only get like 10% of the bandpass at one time. So you have to, the way I talk about it is like a telescope with a coronagraph, it's not a point and click observation. It's a point and click and click and click. And each click you're doing is like a different wavelength. But if you're doing the interferometry in the mid-IR, my understanding is you basically get the whole bandpass for the observatory all at once, which gives you a huge advantage there. I don't know if Sasha wants to talk to that or not.
Yeah, I agree.
So given the fact that HWO is decades away from flying, and given the fact that we're seeing very big mirrors lofted into space, are we remiss in considering the possibility of monolithic mirrors to help solve some of these problems that you've described? Is this a case of if you've got a hammer, everything's a nail? What kind of internal debate goes on when you think about the trades between what you know with the segmented mirrors and a monolithic mirror?
Things. I think, the hammer nail thing is a fair point. I think the other thing about hammers is if you know they work, it's easy to pick one up and use it, right? And one of the, I think one of our biggest challenges beyond the technical challenges that I talked about today are honestly programmatic ones. Just to be honest, like let me set NASA aside for a second. Like when I say our track record in building big complex things as a species, as a civilization, it's terrible. I mean, I'm not just talking about space telescopes. I'm talking about any complex project. It could be hosting the Olympics. It could be building any infrastructure project. Big complex things are hard to do, and they're even harder to do on time and on schedule and on performance. And there's a lot of strategies that we can adopt to make it more likely that we deliver the promised performance on schedule and on budget. One of the things you can do is you can utilize the technologies, I heard it calls like a frozen expertise in the form of the technology in your planning. And that's central to a lot of our thinking, right? So yeah, it is a hammer and a nail, but it's a hammer that we have a high confidence that's going to work. Now, that said, that's not to say that we shouldn't just toss out the idea that you can do wonderful stuff with monolithic telescopes, or that it could be a part of this. I think the challenge with the so that's one of the reasons. There's a separate reason, which is if we want to do some of the other areas of astrophysics that I spoke to, that a lot of those require very large apertures, not 4-meter monolithic mirrors, but 6, 8, maybe larger mirrors. And right now, we don't see that as being something that's got that technological readiness like the segmented mirrors of that size class would have. That might be different in the future. And I know there's various technologies to get monoliths up to that size, but right now, that's not something we're ready to rely upon. If coronagraphs for segmented apertures do not end up developing technologically, because that's our main technical challenge with the architecture we're talking about, is the interplay between that ultra-stable primary mirror, the segmented primary mirror, and the coronagraph that works in concert with that. If that shows to be not something that's working technologically, having a fallback of monoliths or having a fallback of star shades with a monolith or a segmented mirror, those are some things that would be there and on the table, I think.
I'm really glad to see what I perceive to be as redundancy. So you've got JWST and Ariel, for example, life and habitable worlds using different technologies even, and it's so nice to have validation from other instruments. So I'm on the one hand thinking, oh, we should collaborate and divide and conquer and figure out how to maximize the science output. But on the other hand, I kind of like the blind experiment, independent aspect of it as well. With JWST, we're going to be making strategic decisions soon about how to use some very valuable director's discretionary time. I do think that JWST will observe even something like 500 plus exoplanet atmospheres over its lifetime. So it will provide demographic information. So the question for Giovanna is if you've thought from the aerial side about how to kind of seek complementarity. And then a similar question for Sean and Sasha. I'm really worried about small sample statistics. Like I honestly don't think that we'll be able to do occurrence rates in the way that you're saying, just because of root N errors. So I'm looking for ways to beef up the statistics, because I think the number of living worlds will be a small fraction of the number of exo-Earths that we observe. So I guess my question for you two is, are there ways that, obviously it would be great if we could beef up the statistics, but if not, are your samples actually really overlapping? I think, Sean, for habitable worlds, it's something like 25 exo-Earths, and I thought you, Sasha, said 40 super-Earths. No. Okay. Could you clarify that a little bit and, just talk about the statistics a little more?
Okay. I'm happy to start with your question. That's an excellent one. I'm also a great fan of redundancy because, in particular, when you're talking about space missions, there are many things that we need to understand, not just for the technology, but also how we calibrate things, what kind of strategy we are doing for the observations. And so if there is a bit of redundancy, it's certainly for the better. Certainly for aerial, we were, first of all, expecting, in any case, that James Webb would do fantastic contribution to exoplanetary science. And so we have been thinking about how to be complementary and work in synergy with Webb since a lot of time. And in particular, what we are hoping for at this point, given that Webb is so successful, but also there is the expectation that Webb might last for 10 years or even more, how we can plan the observations maybe simultaneously between aerial and Webb. So we've gone this far to think about it. So the more Webb is doing, the better it is for us, because let's be clear, at the moment the lifetime of the mission is normally 4 years. It's just the cost that is limiting that. There is nothing that in principle should stop also on the aerial side, so we can keep going. And if we look at all the science objectives that we want to address, there are so many more that actually we can really do. Even just doing 1,000 planets in 4 years, we already need a pretty, quite careful strategy of observations in order to do that in the lifetime of the mission. And so, even Webb doing the entire program of aerial as we think about it today, in reality, we have so many extra questions that we want to address. If Webb is able in the sense that, we, meaning the exoplanet community, is able to get so much time out of the TAC, that would be fantastic, because first of all, I would expect there are so many new questions that all of a sudden are on the table. At the moment, aerial has been planned in a blind way, meaning if we don't know anything about these planets, or as far as we know today, this is the strategy. But the more we will know about these planets, the more our questions and therefore our strategy will change accordingly. And so, for instance, some of the ideas that have been put forward are, in the case, for instance, that Webb is focusing a bit more on small planets, then, of course, we need to make sure that we are a bit more complete on the other parameter space. If Webb, on the contrary, is doing much more of a survey, including also the giants, then perhaps we can spend a bit more time on these smaller planets because they are time consuming. And so this is where we're looking at. We certainly want to do a lot of phase curves. And although hopefully also James Webb will do phase curves, they are quite expensive in terms of telescope time. So these are just some of the ideas, but it's to say that the more the better. So if James Webb is able to do many planets, this is really fantastic news for us, because we can repurpose the mission in order to be complementary and even more synergistic with Webb.
Maybe I'll go first, Sean. Okay, okay. Maybe just picking up from James Webb and Ariel. I think what would be very, very important, and maybe for the questions here, one of the single most important result could be the pure existence of atmospheres of rocky worlds around M-type stars, right? We don't know whether those atmospheres exist. We heard why it should be complicated or could be complicated, that they don't have any atmosphere at all. But if James Webb and or Ariel could show indications that they can retain atmospheres, this, at least to me, and maybe some would agree, this would open up a completely, additional parameter space for the search for habitable worlds, right? That would clearly indicate that worlds around low-mass stars are also interesting for follow-up. And this is, now coming back to the LIFE mission, very important, because LIFE in principle has the capability of looking for planets, rocky planets around M-type stars. There's of order 70 of M-type stars within 5 parsecs only. And knowing that those planets are of prime interest, you could prioritize those targets in the early phase of a mission, for instance. And then coming to the synergies with HWO, actually we're in very good exchange with our colleagues in the US concerning yield estimates now and also characterization. So we actually started a joint project to understand with atmospheric retrievals how much more you could learn if you had data from both kind of missions, going back to the point that we have to have complementarity, right, in as complete picture as possible, but also in terms of yield. So we are very well aware of the target stars that HWO has. They are the same that we have. We have more lower mass stars in our sample, but going through those numbers while we are maturing the technology and making sure we understand the synergies between the missions with the hope to increase, from a low number to maybe numbers that also you would feel more comfortable with. I think this is part of the ongoing activities that we would be very happy to engage with the colleagues on the HWO team, making sure we understand truly how many plans are needed, that everyone feels comfortable, and where are the synergies, also maybe from the operational part, because we think, last point, we think right now in terms of characterization, but just imagine you have both missions flying around the same time. There could be lots of synergies also during operations, right? You do not have to follow up a planet multiple times with HWO if you had a mid-infrared point already. So those kind of things, right, would automatically allow you to spend more time on other stars, finding more planets, and getting more combined information. I think these kind of thought experiments we should really pursue in the coming years as while we continue looking at the technology as well.
Thanks very much.
Yeah, I have a question that I think it's probably for you, Sasha, but others can answer. Having had some experience of trying to fly things in formation, it's grossly hard. Why not put these on the lunar surface?
I get this question sometimes, and I had different answers why you may want to do it and you may not want to do it. So let me give you the why you may not want to do it. I think in the next years, we will go back to the moon and we will have people on the moon. I'm not sure whether the first priority would be to put an infrared interferometer on the moon. I'm not sure this is going to be the first priority. This doesn't mean it cannot happen in the long run. Then I'm not sure how difficult the environment will be in terms of dust. So this is, I think, one issue. And I also heard people, and this goes back to the Darwin time. So to those of you who have been around for longer already, 20 years ago, similar concepts have been studied already in the NASA side, TPFI, and the European side, which were called Darwin. And they also looked at the moon. And there was one report that says it's not stable enough, that it is actually too, seismologically? Yeah, not stable enough to control the wavefront at a precision that would need it for nulling interferometry. So that a space-based approach would provide a stable environment. And if you now consider cost, I'm not sure which one would win. And also how many planets you could get. I'm not sure whether the lunar surface gives you more access to more planets in the long run.
I guess agree with both. Well, that's what this evening by the pool is for. Is this debate? Is the rest of this debate? Okay, we have only.
Did Sean raise his hand if we have the 30 seconds?
Sure, go ahead.
Spirit of that question, and I think it was the same questioner that asked the one about launching large weight monoliths into space. I love this because part of what we need to be thinking across all these areas, whether it's ground or space, whatever the size is, how do we leverage the technologies that are going to be around 5, 10, 15 years? One thing I didn't get to in the talk is the serviceability that we're anticipating is going to be around that can help refuel, extend the lifetimes. Natalie, that's one of the ways that we could potentially boost the sample size, probably not to a level you're happy. But there's a lot of things that are happening in terms of the ecosystem that we anticipate is going to be in space 10, 15 years from now at HWO launch or at a life launch that we absolutely should be incorporating into the thinking and the design of these things.
So we have 3 seconds left, but since we've had a core group of people stay with us online all the way through, and I'd like to get to just 2 of the questions from the online community. We'll try to keep them quick, and if you could keep your answers brief. So one of them is from Jill Tarter, a question to Giovanna. She says, "What sets the lifetime of the Life mission?" I know a part of this question was already asked, but
the cost of the operation. Sorry, can you hear me? Is the cost of the operation, Jill, 10 million per year at the moment in the current costing. We have planned for years, but it's already understood that if the mission works well, we should be able to go to 6. That's sort of normal for ESA mission to continue. And if it's really working well, then of course we will do our best to make the case. But there is nothing that in principle should stop working.
Great, that's a very promising answer. And then the last question I'm going to take is from Catherine Denning, and I think this is a question that is actually really relevant to all of us, and perhaps each of you could give just a short answer on it. She says, there's a great deal of public interest in the potential discovery of extraterrestrial life, but the actual science isn't always easy to explain. When you're describing your upcoming missions to people who are not experts in these fields or not scientists, what are the points that are hardest to explain or are most commonly misunderstood, and how do you get around that? So perhaps each of you could just give a few sentences on this.
I can start. People often think that we've already taken these pictures because we show so much art, so many renderings of planets around other stars. So we have to keep reminding people that those are just artist conceptions, and we don't have those pretty pictures.
Yeah, especially when it comes to high contrast imaging, even within astronomy, I think people are surprised to hear that the HRI 799 4-planet system isn't the norm. That's one of the few multi-planet systems we've directly imaged.
I'm going to give a counterpoint, which is that maintaining the public interest is really important. And as one of those people who's probably misunderstanding the technical stuff, just give a recommendation to not be so precious about some of the correctness when communicating very broadly. I think even though within like internal community, it is quite important to be correct about the science. But maintaining that public interest through art, through broader translations, I guess, of your work is super important. So, yeah.
The fact, but for the moment, when we're talking about habitable worlds, we are basing this sort of analysis on very limited number of parameters. So we need much more in order to say whether a world is really habitable or not. And so I think we need to do perhaps a bit of a better job to make sure that the public is understanding that, most of the time we don't know if a world is really habitable or not based on the very few parameters that we have.
I think nulling interferometry, even for semi-expert audiences, is a difficult thing to explain. So we always try to say it's like you combine a lot of several telescopes so that it works like a big one. So this is one way out, and it's maybe not sufficient, but that's how we try it. And the other thing we always have to remind the public is that when you say you take a picture of a planet, it's indeed, as Sean was saying, it's a pixel in the end, right? So they think of the beautiful images that we've seen from Earth or the solar system planet. It's not like this, and this is always confusing, right? That you try to deduce all the information from a single pixel, and this is also sometimes difficult to get across.
Yeah, I agree with many of the points said. One thing that I find very deep-rooted in the public psyche is the reason behind why we do what we do, especially when it comes to life or finding a habitable planet or searching for life. Sometimes people think we are doing that because we want to go there. Maybe some of us do think we want to go there, but we sort of know the practicalities of that. The odds are very well against us. So it's hard to convince public that we are doing this as a fundamental quest for understanding the universe, understanding life out there, just as a curiosity, the scientific curiosity. That is hard to convey somehow to the public. And I think we need to do a better job at saying why this is a fundamental part of the scientific process and doesn't always need to have a practical element. And the other thing is, when we spend billions of dollars on these missions, I've had in talks, public talks, people come and ask me, why actually do we want to spend that much money on this? And that again goes back to trying to educate people on why it's so important to our society, to our species, to understand these things at a deep level.
When I come from the direct imaging community mainly, and it's true, when we show one image of an image planet, people sometimes may be disappointed because they have seen these very nice images in the press. And you say that they mix with solar system planets, but often they also mix with the artist views that they see in the magazines. And for instance, if you take the TRAPPIST, 7 planets, you go on the press and you see many very nice images. And when I give conference, I always say, well, you have these images on the one hand, but the reality, what we have at hand, is these curves. And I think it is important to educate people so that they really know what we do. We just don't want to make them dream, but well, at least we want to make them dream on what we want to do, what we will do in the future. But I think we have to be very clear on what we know today. Sean?
Yeah, everything everyone just said. I think the other one that if I had like a way to just like transfer the thing in my head to someone else's head that I wish could just like happen, it's the connected nature of the things that we're doing. And by that, I mean like the relationship between what we're learning in the solar system and what we're learning on exoplanets, and ultimately what we're going to learn about our own planet by studying exoplanets. And, that goes from today, like a lot of our expectations are based on the same literal physical numerical models that we use to predict what's happening to our own planet from climate change. And whatever we're wrong about in those predictions are going to have an impact on how we think about our home world. And I wish there was a better understanding of just how rigorous that science is about what's happening to our own planet, and a better appreciation for how solid that grounding is, because ultimately that's the same foundation that we're talking about. So I think that for me, that would be the one.
Okay. So I think we will stop here. I would like to thank again all our speakers this afternoon. Thanks again.